let us now go back to our example 1. So, and we would like to see how to solve the same example for which we did not even get the extremal. So, I am talking about the example that we discussed right in the first slide with the extremal given as follows, right. So, my function f is y square 1 minus y prime square. So, in example 1, my f of y comma y prime is y square 1 minus y prime square, and we saw that. So, in this case my p, which is partial f partial y prime, will be equal to negative 2 y prime square, well, negative 2 y square 1 minus y prime, and my Hamiltonian h is y square 1 minus y prime square, right. Okay. So, using my Beltrami identity, I see that I get two equations, either y is equal to 0 or y is equal to x plus a. We have seen that in our in the discussion of the solution to this example. We are right now assuming one of the results, x is equal to x plus a, right. So, well, of course, these are all valid solutions to my Euler-Lagrange equations, right. Now, but they do not simultaneously, neither of them simultaneously satisfied the boundary condition. My boundary condition was, recall that my boundary condition was y of minus 1 is 0 and my y of 1 is 1, right. Okay. So, then, so now we are going to look for so what have we got? So, let me call this as my solution A and call this as my solution B, right. Now, notice that if we find my momentum and Hamiltonian for both A and B, right, we can show that the momentum and the Hamiltonian both are 0, right. So, for both the solutions, the momentum and the Hamiltonian are 0. So, which means that we do not have to worry about the Weierstrass-Erdmann conditions, because they are satisfied from the left and from the right, they are satisfied trivially. Right. So, what have we got here? We have got the following. So, now we have two functions. So, note that y, the solution A, y is identically 0, satisfies the left boundary condition. That is y at minus 1 equal to 0, satisfies this boundary condition, right. And my solution y equal to x plus a satisfies the boundary condition y at 1 is equal to 1, provided a is equal to 0. So, my extremal in this case is y is equal to x, right. So, let us draw the figure. So, we have the rectangular hyperbola. This is my first boundary point and my second boundary point is 1 comma 1. So, we have two solutions, one is y identically 0, the other is y equal to x, right. And these, we have to construct a broken extremal such that the extremal joins the 2 points under consideration. Now, note that, so let me call this as my solution from the left, or so my broken extremal is such that my solution from the left is y1, which is this, and solution from the right y2 is x, well, y2 will be this one, y is equal to x, right. Now, my continuity condition of the broken extremals will give me that y1 at x star will be equal to y2 at x star. So, there at x star, the corner point, the solutions must match. So, I get that 0 is equal to x star from here, right, or the solutions match at 0. So my extremal is as follows: from -1 to 0 we have y1. So from this point to this point we have y1, this solution, and from 0 comma 0 to 1 comma 1 we have y2. So this is my, so my broken extremal y, my broken extremal y is 0 when x is from -1 to 0, and it is x when x is from 0 to 1, right. So this is my broken extremal solution to this problem, right. So we have at least found an extremal which satisfies the Euler-Lagrange equation and also the Weierstrass-Erdmann condition. So now how, let me just summarize our discussion in this topic by saying that how to find these class of broken extremals. So the general strategy is the following: we solve Euler-Lagrange, we solve our Euler-Lagrange equation, we look for solutions satisfying the boundary conditions, right. Those solutions could be different from each other, and then for different solutions we match the solution at corner points. At corner point, let us say there is just one corner point x star. So we match it by y1 of x star is equal to y2 at x star, and then we also satisfy the Weierstrass-Erdmann condition, and finally we allow the problem in general can allow for more than one corner point, for more than one corners, right. Okay. So now let us look at a very interesting example in this family of broken extremal, namely the example of finding the extremal for the Newton's aerodynamic problem. Okay. The example I want to discuss is regarding Newton's aerodynamic problem, right. So what exactly is this problem? Now physically we have seen, when we drive cars, we have seen that the cars are designed in such a way that their front shape, almost 90% of the design is such that the front shape of the car is all slanted, right. And also when we look at some of the other vehicles which move through the air, like the aircraft, like the rocket, we will see that almost all of these vehicles, they have a slanted body at the front, and that is because so as to reduce the frictional drag or the resistance of the air, right. So we are, in this lecture we are going to derive the shape of these objects which move through the air, right, by looking at the frictional drag which acts on the surface of these moving objects. So the Newton's aerodynamic problem says to find the optimal shape, let us say, of rocket's nose. So this is just one object, rocket's nose cone, which creates least air resistance, right, passing through the air. Okay. So assumptions in this problem: assume, we have couple of assumptions. First, air is thin, which means that we have perfectly elastic particles. We will see what is the implication of these assumptions. Perfectly elastic particles, especially when we have the collision of the air particles with the object which is moving through the air, the collision is perfectly elastic. So then another assumption is that the particles bounce with equal speed. Particles, when they move, the air particles bounce through the surface with equal speed, equal speed, and we ignore the tangential friction, and then we also ignore non-Newtonian effects. We also ignore non-Newtonian effects like the compression of air, rarefaction of air, and so on, right? Non-Newtonian effects like compression of air, right? Okay. So then with this assumption is not with this assumption we have not simplified too much. This assumption still holds for problems where the object is moving in a very thin atmosphere. So realistic cases under this assumption follows objects moving through thin atmosphere like high altitude motion where rockets move. So motion, so realistic at high altitude where and with supersonic airspeed typically of the order of Mach number 5 to 10, right? So again typically of the order of the speed where the rockets move. So then I have further assumptions in order to set up the problem. So further assumptions, we assume that, note that when the rocket moves, it also rotates about its vertical axis, right? To provide stability, the rocket while moves up through the air, it rotates, which means that the shape will be such that it is symmetric about this length axis, right? So as the rocket rotates along its length, it implies that the cone is circularly symmetric, right? The cone is circularly symmetric. We reduce the problem to determine the profile of the nose cone. So reduce problem to determine optimal shape of nose cone. The rest of the body we do not care because that will be more or less cylindrically will be cylinder, right? Okay. So then another observation is that the cone is such that it has a radius r at its base. So I am just specifying some dimensions of the object and length L, right? So which means that at the base the radius of the cone is r and the length of the cone is taken to be capital L, right? That will give us the boundary conditions. And also we also assume that the shape of this cone is convex, right? Or it means that the interior angle of this object is, let us say we draw the interior angle, this angle is less than this angle phi that I am saying, it is less than 180. The interior angle phi is less than 180 degrees. And finally, we also have that the profile of the cone must be non-increasing, So what I mean to say is that when we find out the slope of the shape is negative, right? And that follows from assumption 7 that the shape is convex. Okay. So with this I am ready to set up the problem. Now suppose let us draw this figure. So I am talking about let me draw half the figure here. So, this is my x axis, this is my y axis, and let us say this is my length L of the cone, and this is my base radius r. And from here, let me take any point which has a radius x, and also let me draw the tangent to this point, right. So, the tangent to the point, and let me do some geometry here. So, this is the horizontal and my vertical is as follows, and also let us say if I have an air particle which is hitting the surface of the cone, let us say it makes an angle theta, then by geometry I have that this angle is also theta, but it bounces off with the same angle. So, this is also theta, right. So, if this is my V, then this will be also my V, right. So, I am just using all the assumptions that I have just stated in the problem. Okay. So, I am ready. So, let us say the component of V along this direction is S. Okay. So, I am ready to write down the functional. So, note that, so first of all, it is irrelevant whether we move the object or the medium, right. We can keep the object fixed, medium moving, or medium fixed, object moving, to look at the problem. So, we assume the latter, that the medium is moving, right, assume latter. So, then also we have to figure out what is the tangent to the surface. The tangent to the surface is y prime, right. So, y prime will be the tangent to the surface is the tangent with respect to the vertical angle, right. So, y prime is equal to this the way it is constructed is tan phi, or this is tan 90 minus theta, right, and this is also equal to it is also equal to cot theta. Well, let me call this tangent, let me say that the tangent has a negative sign because it is a decreasing slope. So, what I get is that cot theta is equal to negative y prime. So, that is what I wanted to say. And then, since my angle of incidence is equal to angle of reflection, that is this theta is equal to this theta, right, and this is because of perfectly elastic collision. This means that the angle between the reflected particle and the vertical, so it implies that the angle between reflected particle and the vertical is 2 theta. The angle between the reflected particle and the vertical is 2 theta, and we can see that also from the diagram the velocity component along the vertical is S, right, and we can see that S, which is also equal to V cos 2 theta by the construction here, right, or this is also equal to V 1 minus 2 sin square theta, right. So, which means that the change in the velocity is the initial velocity minus the final velocity, and I get that this is also equal to 2 V sin square theta, 2 V sin square theta. Okay. So, which means we can write down the total force or the frictional drag which is acting on the surface. So, the total resistance force, and this will be per particle per particle per unit area, right. So, the total force is mass times acceleration, Newton's second law, and that is equal to mass times the change in velocity, which is 2v cos 2v sin square theta, right. So, that is my net force, and so this is also equal to 2 mv 1 by 1 plus cot square theta, which is also equal to 2 mv by 1 plus y prime square. That is how we have defined cot square theta. Okay, so then notice again the figure. Well, notice again the figure that that we have a lateral surface area. So, we have to figure out the total force. The total force will be force per unit area that we have, unit length that we have just found, times the integration over the length. So, along let us say one element dy has a perimeter. So, the perimeter or the lateral surface area along the element dy is 2 pi x. This is a circle of radius x, right. So, which means my lateral surface area at radius x is 2 pi x times dy, right. So, 2 pi x dy, which means my total force will be the sum over the will be the integral of this force per unit particle per unit area times the total area. So, f of y is given to be integral from 0 to L, well y is from 0 to L, 2 pi x dy times 2 mv by 1 plus y prime square, right. So, coming from this and this respectively. Okay, so, I can club everything together, I get 2 pi times 2 mv, these are all constants, integral 0 to L x dy divided by 1 plus y prime square. Now, let us take this constant to be just 1 without loss of generality, because they are not going to determine, these constants are not going to determine the optimal shape. So, we have to optimize this particular functional, right. So, let me call this quantity here, which I have circled as my integrand f. So, we need to write down, to find the optimal shape, we need to write down the Euler-Lagrange equation for the integrand f of x comma y prime, which is x by 1 plus y prime square, right. So, when we do that we have d dx of partial f partial y prime minus partial f partial y. There is no function of y in f, this is set equal to 0, and I get that from here I get that x, well I get that x y prime, well 2 so 2x y prime 1 plus y prime square whole square is equal to a constant C1. I have integrated once with respect to x. So, this is my equation that I have to solve to find the extremal shape, right. To solve that, let us now, so what I have is the following. So, this means that my x is C1 by 2 times 1 plus y prime square. So, it was y prime square, yes, whole square by y prime, right. Okay. So, let us now introduce new set of constants. So, let me say that C, my constant C is C1 by 2 and my function u is negative y prime, right. From here what I see is x is C times 1 plus u square whole square. I just substituted these new functions and new constants, and let me open it up. I get that this is also equal to 1 plus, well I get this whole square divided by u as well. So, divided by u, and this can be simplified to see that this is u cube plus 2u u cube plus 2u plus 1 by u, right. And so x is, so this is x in the form in terms of the parameter u. Similarly, I can write my variable, my coordinate variable y as a parameter of, as a function of u. So note that y prime, which is dy dx, which is also equal to dy du times dx, well, we want to find dy du, right. So dy du is dy dx times dx du, or this is also equal to y prime times times x prime of u, but y prime is negative u, right, and x prime u can be found from this relation. I see that this is also equal to c times 1 by u minus 3u cube minus 2u, and then from here I can integrate to get y as a function of u, which is d plus c times log u minus 3 by 4u minus u square, right. And I can write down x of u, which we have found earlier, as c times u cube plus 2u plus 1 by u. So this is my parametric representation of the extremal for both the components x and y. Let me call this solution as A. Now notice that u is negative y prime, and since y prime is decreasing, this will always be positive. So from here and from this condition, I can immediately deduce that x of u will always be positive the way u is chosen, right. So which means that x equal to 0 cannot be a solution, to my Euler-Lagrange equation, right. If we were to draw again the shape of the cone, right, so the cone has length L and the total length along. So if we were to draw the shape of the cone will be such that the profile never hits x equal to 0, right, which means that the profile given by A will be such that it will never hit the y axis. So which means we can take two profiles, one as y1, the other as y2, right, and the profiles, they match at, let's say, a corner point x star, and let me call this as x of u1. We need to find u1, and this is x equal to r, which is at x at u2, some other parameter u2, right. Okay. So what is the conclusion so far? The conclusion is, since x equal to 0 is not a solution, it implies we use the idea of broken extremals to find out the solutions, right, to find y1 and y2. Let me again draw the figure. So we have y1, let's say, of this profile and y2 of this profile, and they match at the point x star, and this is x at u2, which is equal to r, and this is x star, which is also at x at u1, right. So what have we got? We have broken extremals y1 and y2 such that, notice that this length is L, such that y1 at 0 at x equal to 0 is L, and y1 at x star is equal to y2 at x star, and we also have y2 at x equal to r is equal to 0, right. So we can take the profile as follows. We can take y1 to be the flat profile, we can take y1 to be, well, we can take y1 to be the flat profile, right, that is y prime is equal to 0, and the reasoning for taking a profile like this is, note that y prime, the way we have made our assumptions that y prime has to be non-increasing, right. So, if y prime is not negative, it cannot be positive, it can only be 0. That is what we are left with. So that the shape is a convex shape, right. So, for convex shape, okay. And then we can take y2 to be the profile given by my Euler-Lagrange solution A, right, or this is arrived from the Euler-Lagrange equation, right. Okay. So, then so what have we got? So, at x star, note that at x star, the point of continuity, we also should satisfy the Weierstrass-Erdmann conditions. So, at x star, Weierstrass-Erdmann corner conditions must be satisfied, right. So, which means that h of x star at x star minus must be h of x star at plus, right, from the left must be equal to the right, where my h is this Hamiltonian function y prime del f del y prime minus f, right. Okay. So, this question is, what is this h? So, notice that h when, so my f is the following function, recall in this aerodynamic problem my f is the following, it is also equal to x by 1 plus y prime square, right. So, when we plug this, we get my h function to be negative x by 1 plus y prime square whole square times 3 y prime square plus 1, right. So, which means that h of u, in terms of u, I get that this is also equal to minus x times 3 u square plus 1 divided by 1 plus u square whole square, right. So, now h of u at x star minus. So, from the left we have the profile is horizontal. So, we can plug that. So, what have we got? At x star minus, from the left I have the profile is flat, right, or my u is 0, which means that h from the left is nothing but x by 1 plus u square whole square by 3 u square plus 1. I plug in u equal to 0, I get this is also equal to x star, right. So, this is x star minus. Now, at x star plus, we have the full profile. So, y prime is not 0. So, I get that h at x star plus is minus x star 3 u square plus 1 by 1 plus u square whole square. So, I equate these two quantities, right. So, to see that, so which means that h at minus will be h at plus at the corner condition x equal to x star, and I see that my solution that I get is 3 u square plus 1 by 1 plus u square whole square, and this is equal to 1, right. So, from here I can solve for u, I get u equal to 0 and plus minus 1, right. U is equal to 0 or plus minus 1. Okay. So, now this question is, what is the value of u? I know that u is positive because the profile is non-increasing, because u is minus y prime, right, and this must be positive. So, we take my u to be 1. So, this is my value of u1. So, my x star is x of u1, and then we plug the value of u1 to find what is x star, and that will be my corner point. So, finally, we have, so notice how many conditions we have in the problem, how many constants. We have constants like d, constants like c, constants like u1, u1 here and constants like u2, right. So what have we got? We have four unknowns, right. We have u1, u2, c and d, and we have four equations. We have four equations given by y of 1 is L, x of u2, well, so this is y of u1 is L, x of u2 is equal to r, and well, what else? Y of u2 is equal to 0. Well, I already know what is u1. u1 is 1. So we have three conditions. three unknowns and three equations, and hence the system is fully determinable, right. I want to end the discussion on this topic by mentioning that what have we got? The shape that we have got of the cone profile is a profile of the following. We have got a shape like the following, where it is flat at the top, right. So the shape is like so the shape is like a frustum of a cone, or the shape of a cone which is in between two parallel plates, right. This is also the famous shape of hemiplates. This sort of a profile is also known as hemiplates, which is commonly found in bullets, which also move in the limit of high Mach number range.